In this video, I'm going to show you what is a separable differential equation and how we can solve separable differential equations. A differential equation is separable if we can write it in the form of f of x dx equals to g of y dy. So if we can separate the variable x from the variable y, if we can write in one side of the equation only x and in the other side only y, then we say the differential equation is separable. And for solving these type of differential equations, simply we can integrate the two sides of the differential equations. By calculating these integrals, we can find the solution of these type of differential equations. Let me show you some examples. Our first example is dy over dx is 2x plus 3 over 3y squared. The first step is to try to write this differential equation in the form of f of x dx equals g of y dy. We have to try to separate variables x with dx to the one side of the equation and variable y with dy to the other side of the equation. Here, with cross multiplication, by multiplying 3y squared by dy and dx in 2x plus 3, we can separate variables x from variable y. So if we multiply 3y squared in dy, we have 3y squared dy equals to 2x plus 3 times dx. Now the differential equation is in the separated form. Variable y is with dy and x is with dx. Now for finding the solution of this differential equation, we have to integrate the two sides of this equation. So for finding the answers, we integrate from the left and we integrate from the right side of the equation. Integral of 3y squared is 3 times y to the power of 3 over 3. Based on the power rule, integral of y squared is y to the 3 over 3. If we cancel this 3 from the bottom with this 3 from the top, so integral of y to the 3y squared is y to the 3. Integral of 2x is 2 times x squared over 2, which if we simplify it, it's x squared. Integral of 3 is 3x, and don't forget to add the constant c to one of the sides of the solution. Usually we are adding this c to the side that has variable x, but you can add this c to the other side of the equation. And so this is the solution of this differential equation. If we want, you can leave your answer in this implicit form, or if you like to find y explicitly, you can find y from this equation. If we take cube root from both sides of this relation, we can write y in the form of cube root of x squared plus 3x plus c. So you can write the solution in this form as well. This form is the explicit form and this form is the implicit form of the answer. And note that we cannot find the constant c in this equation because we don't have any initial condition for this differential equation. Let's do another example. The differential equation is x dy minus 1 plus y squared dx equals 0. The first step is to try to write this differential equation in the form of something of x dx equals something of y dy. So note that the coefficient for dx should be f of x and the coefficient for dy should be g of y. But here in this differential equation, the coefficient of dy is x and the coefficient of dx is y. So we have to try to write it in the form of a separable differential equation. So we have to try to bring this 1 plus y squared close to dy and this x close to dx. To do so, we can move this term to the other side of the equation. So first we write this in the form of x dy is 1 plus y squared dx. Now we can bring this to the denominator of this expression and we can bring x to the denominator of dx. So we can write this differential equation in the form of dy over 1 plus y squared is equal to dx over x. Now the differential equation is in the form of a separable differential equation. F of x with dx, f of y with dy. Now for finding the solution of this differential equation, we have to integrate from the two sides of this equation. So integral of dy over 1 plus y squared equals integral of dx over x. We know that integral of dy over 1 plus y squared is tangent inverse of y. This is one of the formulas of integral. Integral of dy over 1 plus y squared is tangent inverse of y. And integral of 1 over x dx or dx over x is ln of x plus c. Don't forget to add c to one of the sides of your answer. So this is the solution of this differential equation. But if you want, you can find y explicitly. To get rid of this tangent inverse here, we have to take tangent from the two sides of this equation. So we can write our answer in this form as y is tangent of ln of x plus c. So this is another form for the solution of this differential equation. It's up to you to leave it in the implicit form or write your answer in the explicit form. Let's do another example. Y prime is tangent of x times tangent of y. First step is to try to write this in the form of f of x something of x times dx equals to g of y dy. Note that y prime is actually dy over dx. If instead of y prime we write dy over dx equals to tangent of x tangent of y, now we can bring tangent of y to the denominator of dy and we can bring dx to the top. So we can write this in the form of dy over tangent of y equals tangent of x dx. Now our differential equation is in the form of a separable differential equation. The expression of y is with dy and the expression with x is with dx. For solving this differential equation, as usual, we have to integrate from the two sides of the equation. If we integrate from the left and right side of this differential equation, we have integral of dy over tangent of y equals integral of tangent of x dx. First, let me show you how we can find integral of tangent of x. In differential equation, we see the integral of tangent of x dx repeatedly. So I highly recommend you to memorize the integral of tangent of x dx, which is actually ln of secant of x. I will show you why the integral of tangent of x dx is ln of secant of x, or actually negative ln of cosine of x also. Note that we can write tangent of x as sine of x over cosine of x dx. From trigonometry, we know that tangent of x is sine of x over cosine of x. Now for finding this integral, we can do a simple u substitution. If we choose u to be cosine of x, du is negative sine of x dx, which we have this here in numerator. If we substitute the integral in terms of u, the denominator is u and numerator is actually negative du. Note that sine of x dx is negative sine of x dx is du, so sine of x dx is negative du. And this integral equals negative ln of u. And u is cosine of x, so this equals negative ln of cosine of x. So this integral is equal to negative ln of cosine of x. And usually it's better to put absolute around cosine of x. But note that also you can write this answer in the form of ln of cosine of x to the power of negative 1. We can bring this negative to the power of this, and cosine to the negative 1 is 1 over cosine, and 1 over cosine, cosine to the negative 1 is 1 over cosine, and 1 over cosine is secant of x. So we can write this in the form of ln of secant of x. So integral of tangent of x dx is negative ln of cosine of x or ln of secant of x. You can use this or this for integral of tangent of x. But how we can find the other integral here? What is the integral of dy over tangent of y? For finding the integral of dy over tangent of y, note that 1 over tangent is cotangent. So we can write it as cotangent of y dy. And cotangent is cosine over sine. Similar to the integral of tangent of x, if we do a simple u substitution, if we choose u to be sine of y, du is cosine of y dy, which is the numerator. So this integral equals to du over u. And integral of du over u is ln of u. And because u is sine of y, so this equals ln of sine of y. So integral of the other side of this equation is ln of sine of y, or ln of absolute of sine of y. Let's continue solving this differential equation. So integral of dy over tangent of y is ln of sine of y, and integral of tangent of x dx is negative ln of cosine of x. Usually we are not putting these absolutes in these differential equations. Plus c. Do not forget to add constant c to one of the sides of the answer. So this is the solution of this separable differential equation. But actually we can write this answer in much better form and more simplified form. Let me show you how we can simplify this answer. First, let's bring negative ln of cosine of x to the other side of the equation. Then we can write this as ln of sine of y plus ln of cosine of x equals c. We know that ln of any expression plus ln of other expression can be written as ln of multiplication of those expressions. ln of a plus ln of b is ln of ab. This is one of the properties of logarithmic functions in general. So we can write this as ln of sine of y times cosine of x equals c. We know that when we have ln of something equal a, say ln of x equals a, x is equal to e to the power of a. So here, if we use this rule, we can write this in the form of sine of y times cosine of x is equal to e to the power of c. In this way, we can get rid of this ln. So when we have ln of something equals a, that expression equals to e to the power of a. And finally, note that e is a constant. E is approximately 2.7. Euler's number is approximately 2.7. C is also a constant. So all of this is a constant. If we name this constant something like k, we can write this answer in the form of sine of y times cosine of x equals k. And this is the final solution of this differential equation. Sine of y times cosine of x equals k. Let me show you one more example. Y prime equals to e to the power of 2x minus y. Similar to the previous question, first, instead of y prime, we write dy over dx, because y prime is actually dy over dx, equals to e to the power of 2x minus y. Note that e to the power of 2x minus y can be written as e to the power of 2x times by e to the power of negative y. Because we know that when the base are the same, we can add the power. So if we add 2x to the negative y, again we back to the original equation. So we can write e to the power of 2x minus y as e to the 2x times by e to the negative y. Why we change this expression to this form? Because we want to separate x and y. When between x and y we have plus or minus, we cannot separate x and y. But now here, between these two expressions, we have multiplication. So we can separate the variable x from variable y. This is the reason that I preferred here to write this in this form. Now, if we move this to the denominator of dy and we bring dx to the numerator, we get to dy over e to the negative y equals e to the power of 2x dx. Note that we can bring e to the negative y to the numerator and write it in the form of e to the y. If we bring this to numerator, we can change the sign of the power and make it positive y. dy equals e to the 2x dx. Now that the differential equation is in the form of a separable differential equation, we can integrate from the two sides of the equation to find the answer of this differential equation. Integral of e to the y dy is e to the y, and integral of e to the 2x is e to the 2x. But don't forget, you have to put 1/2 here, because we know that integral of e to the power of ax dx is e to the power of ax 1/a times e to the power of ax. Based on this formula, integral of e to the 2x is 1/2 e to the 2x. And don't forget to add c to one side of the solution. So this is the general solution of this differential equation. But if you like to write your answer in explicit form, if you want to find y explicitly, you can write your answer in the form of y equals to ln of 1/2 e to the power of 2x plus c. How we get from this to this answer? Note that if in general we have e to something like a equals b, then if we want to find a equals ln of b. So to cancel e, we just take ln from both sides, and so a equals ln of the other side of the equation. So we use this rule and we get this answer here. This is another form for the solution of this differential equation. I hope by watching this video you have learned how to solve separable differential equations. If you like this video, please subscribe in my channel, and see you in the next videos.